Welcome back to ECE 220. Your second exam is tomorrow, and that will be covering materials from Chapter 4 and a little bit from Chapter 9, dealing with phasors and complex numbers. How do you analyze some simple circuits with complex numbers? We are in Chapter 6, Group A. Your lab number 2 reports are due today, this evening, and your pre-lab for number 3 is due on Saturday. We've had a last-minute entry into our list of goals. If you were looking at this prior to the lecture, the notes did not include this middle stretching activity. We need to warm. I was going to do it first, and then I thought, well, we might have a few more people in the middle of class, and it'll give us a little bit of a break. We will start with capacitors, which is a dual concept to inductors. If you are feeling comfortable with inductors, you should feel the same comfort with capacitors. If you feel more comfortable with capacitors, great. Now you can use that feeling to help your conceptual understanding of inductors. It's this dual concept that we've been playing with all semester. Current and voltage are duals. MCA and NVA, mesh current analysis and node voltage analysis, which is tomorrow. That's what you'll be playing with on exam number 2, are those analysis strategies. We'll talk about the current voltage relationship of a capacitor, and it's dual to what the current voltage relationship is for an inductor. We'll go through some facts, and then we'll do some stretching exercises. We'll try to get ready before you do something, before you compete. You usually kind of want to warm up. We're competing tomorrow. Exam number 2 is tomorrow. Let's sort of get ready for that with some stretching. And then if we still have time, we'll go through some examples similar to what we did for inductors with capacitors. And then we'll talk about power and energy in an ideal capacitor. You've probably seen these. I apologize, maybe the image is a little blurry, but I expanded it. But you can now see these little cylinders or these little discs populating your circuit board or around different instruments. And we will symbolize those with these horizontal lines. Sometimes somebody might try to differentiate between the different plates on a capacitor. If it's an electrolytic capacitor, you need to pay attention to the polarity, and for that reason you might have one of these lines being curved, which is the negative polarity on that symbol. But we won't worry too much about polarity of a capacitor. We'll just plop them in like they are okay to be inserted, irregardless of which plate is more positive than the other. But in reality, if you are dealing with capacitors that do need to differentiate, you need to make sure you know which terminal or which lead is the positive lead and which one is the negative lead. We get a little loose with that in this class. We don't really worry so much about it. But in reality, you can have things blowing up or exploding if you connect these incorrectly. If you start trying to put a capacitor in and you've put it in upside down or sideways or backwards, it could have some interesting results or interesting consequences. You might get more bang than you wanted to. Practically, as with inductors, there's some dissipation of energy in a real capacitor. We won't really deal with that here. We'll stick with the ideal. We'll just say if we have a capacitor, that's what we have, and if we have resistors, then we'll put those in where we put them in. But in reality, and you could model that resistive behavior of your capacitor either in parallel or series, depending on how you are wanting to represent that dissipative nature of your capacitor in practice. The structure is, this is one structure, but this is the one that's maybe the cleanest to think about, is you have two conductors separated by a dielectric. And you now are pushing charges, you're displacing charges on and off those two conductors. There's no flow through that dielectric. But that displaced current actually produces a conductive current, and so we won't worry so much about no charge flowing through the dielectric. To us, the terminal will look like we have current going through, so we'll just go ahead and assume we have current going through this capacitor, but in fact it's a displaced charge and change of charge that then pushes things around in your circuit. We won't get too into that, but this is the idea, and you can vary the capacitance of your capacitor by varying the geometrical conditions of that construction of your capacitor. You can produce more capacitance or less depending on how you design physically this device. And you could do that with increasing the area, reducing the thickness of that dielectric, etc. But you can now vary the capacitance, and obviously you can have different shapes and configurations to your capacitor. And these cylinders might actually be sort of this sandwich nature rolled up, and then they stick it in a tube. But you still have this capacitive behavior happening between two conductors separated by a dielectric. That's why the disc ones look like maybe what I have drawn with the different conductors on two sides. The cans, what's that? Well, now you take these conductive surfaces, separate them with a dielectric, and then you roll them up and stick those into a can. Try to keep everything clean, meaning you're not compromising the conductors and dielectric properties in doing that. The operation is really this separation of charge. When you have charge separation, then you have an electric field from the plus charges to the minus charges, and that now establishes a voltage. If you now, and the energy is stored in that electric field. That's now dual to where the energy was stored in an inductor. In an inductor, where was the energy stored? In the magnetic field. So that was now in these circular field lines around this current that's flowing. You now can build that up and release it, the energy in your magnetic field. Here you can alter the charge, or then change the electric field to now increase and decrease the energy of that electric field, and that now allows you to put power in and then have power removed from that conductor or from that capacitor. And as I said before, we won't really distinguish between the displacement current and the conduction current. But there's no charge flowing through the dielectric, but the fact that it's being displaced, the charge being displaced on the top plate and the bottom plate, that initiates a conduction current at the terminals, the top and the bottom. I've already forewarned you that we would be talking about ice. Eli the Iceman. Eli has an L in it. That's for the inductance. Ice has a C in it for capacitance. We now can write or recall or remind ourselves of the current voltage relationship of a capacitor if we simply remember ice. And ice now tells us how the voltage and current are related based on a capacitor or with a physical element of a capacitor, similarly to how we used Eli. Here, the first letter is I, that's our current, and that's now equal to the other two variables in the ICE formula, the C and the E. The C is our proportionality constant, and E is electromotive force or voltage. That's now the derivative of that voltage across the capacitor. I is equal to C dV dt. And so you need to remember that, obviously, through this class, through other classes, when you start talking about circuits that contain inductors and capacitors, you need to be able to recall the current voltage relationship. Just like Ohm's law for a resistor, now you have Eli and ice for inductors and capacitors. I is equal to C dV dt. The time rate of change of voltage establishes a current flowing. Now remember the displacement current and the conduction current. We'll just be saying the current through the capacitor, knowing that it's sort of this connection between displacement current and conduction current. We can then do the antiderivative if we want to now write an equation for voltage in terms of current. So now we'll just divide both sides by C, integrate both sides, and now that will allow us to solve for the voltage across that capacitor in terms of the current that is flown through it. Remember, current is just charge per time. So you are playing with charge when you're dealing with a capacitor. And we can't forget the initial condition. The initial condition is important. We'll keep that second term, but now we can solve that equation for the voltage across a capacitor. It's now two parts, just like our inductor had two parts. Now we have this first part, which is the component of the voltage that's a result of the current that's flown from time t0 up to the current time. This is now the voltage component associated with the capacitor due to the current that has happened from time t0, which is when we say we're interested in finding all of this out, to the present time. And what's happened up to time t0 is what's established the initial voltage, the initial condition on that capacitor's voltage. So this second term, V sub C of t sub 0, is our initial condition term. And that's the initial voltage at time t sub 0. And if we really wanted to compute it, if we knew what was happening from minus infinity in time up to now, then we could integrate. If we knew that relative to the current, then we could tell you what the voltage is, but yet typically we just say, oh, at this particular point in time, our initial voltage value, the initial condition on that capacitor is 2 volts. And then we tell you what the current is from that point on. But if we wanted to, we could still find this. Obviously, it takes a lot of knowing, because now you have to know what's happened from minus infinity up to t sub 0 with respect to the current. And that's now this 1 over c integral of I sub c of some variable of integration. Maybe I should keep it the same, tau d tau. So you integrate current to get voltage in a capacitor. And what's integrating current? Current is coulombs per second. You integrate that, you're going to get charge. So now you integrate current, you get charge, and that charge separation is what establishes the voltage, and that's the current voltage relationship of a capacitor. Let's work through these facts. What does ice tell us? You say ice, and now you go and you'll order a drink, and they'll go, do you want ice or not in your drink? And so now what you're thinking is, I don't think I want a capacitor today. On the side, yes. So now you say, can you put the ice on the side? And they're looking at you like, what? That's going to cause a mess. Well, put it in a cup or something. I want my ice on the side. Sorry. But you'll remember this. Now when you start talking about ice, you're going to be seeing this differential relationship between current and voltage of a capacitor. You know that I is equal to C dV sub C dt, or the time rate of change of the voltage across that capacitor is what's giving you the current. And where's the energy stored? That's now, because of this charge separation, that establishes an electric field. That electric field, dual to the magnetic field, is what we are now playing with a capacitor. Dual to what we were doing with the inductor. Now we have energy stored in the electric field, and that's our capacitor. This, if you look at the ice equation, I is equal to C dV dt, that hopefully tells you the answer to the next fact. A capacitor resists abrupt changes in, and now you look at ice and you go, okay, what's going to cause problems in this expression? We can't have something being infinite. And to avoid infinity, although we like to go to infinity and beyond, but we won't do that here. You might if you connect your capacitor wrong, and never mind. And where is infinity in ECE? Sometimes that's not that far away. Infinity is 5 time constants, roughly. And a time constant can be very short. So going to infinity and back doesn't take that long. We don't have to be that patient in electrical and computer engineering, because 5 time constants could be fractions of a second. Where was that from? Oh, I'm now looking at small changes. I can make a small change in dV, in voltage, but I can't do that instantaneously. I can't make dt go to 0. If I did, then the current would be infinite, so the capacitor is resisting abrupt changes in its voltage. And now, what does this capacitor look like circuit-wise when it's in a steady state or when we have a DC source? What happens to capacitors? So it's the dual. An inductor looks like a wire. A capacitor is the dual. It now opens up. It looks like an open circuit. Now you would simply remove those capacitors from your circuit if you wanted to analyze the DC behavior or the properties of that circuit in DC with frequency of 0. The capacitor then acts like an open circuit to a DC source. And you'll need to use that here. You'll need to use that in the next class, 320A. If you're now trying to find out what are my initial conditions on these devices, your inductors and capacitors, and you've now maybe established those initial conditions with DC sources, you can find what those voltages are across the capacitor and the currents through the inductor by shorting your inductors and opening up your capacitors. Have to give you another unit. This one is now the farad. With a capital F. That's the constant of proportionality. It's the farad. So now we will be talking about farads, henries, ohms. Those are our 3 circuit elements that we play a lot with in this class. And here's our long sentence that we are going to read. Wow, more than a screen. So I'll expand my screen. Capacitance. This is the property of this circuit element such that when we have a time-varying voltage, remember ICE, I is equal to C dV dt. When we have dV dt happening, then this particular device will have current flowing associated with it. And here I'm trying to spell it out. The time-varying voltage produces this displacement current. It's displacing charge. But that displacement current is indistinguishable from us, from the terminals, as if it was a conduction current. So we'll just say current going through a capacitor when we kind of are winking and knowing that there's no charge flowing through that capacitor, but at the terminals it is establishing current flow. And we get to even go smaller in units now with capacitors. Farad is a big unit. It's quite large, and so many of our capacitors are going to be in the microfarads to picofarads, 10 to the minus 15th farads in their values. That's what C will be dealing with. But now they have created supercapacitors. Super reminds me, what are you already thinking when I say super for tomorrow? Super node, super mesh. So just reminding you, tomorrow is the exam, and you'll have to do some super things on the exam. You'll be playing with super nodes and super meshes. But here, in Chapter 6, well, yes, we will probably be saying, oh, we have a 1 farad capacitor. Well, if you had it with the standard technology with these conductive plates and a dielectric, that might be the size of a football field. But you can now start creating these with the advanced technologies that we now possess, and you can build them and still have them manageable in size. You're not going to be driving around with a vehicle that has a supercapacitor the size of a football field. But now we do have supercapacitors that they allow for quick charge and discharge, and so you can view those sort of like rechargeable batteries. And they're nice for that purpose. You can charge them up and discharge them many, 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 many times, and you can do it quickly. And they have much larger values of capacitance. They can actually be now in the, let me get my units right. Let's say that they go from 1 farad to even in the thousands of farads. But now the voltage that's associated with the separation of those plates is much lower than in these microfarad and picofarad capacitors. Now the voltage range is more like 1 to 3 volts. And so we might have to play with interconnections, and we'll deal with that shortly, maybe not today, but we'll talk about combining these capacitors in series and in parallel to maybe allow us to provide the properties that we need relative to the capacitance value and the voltage that we need to support what we're working on. Okay, it's time for some calisthenics. Let's do some stretching with phasors. This is for tomorrow. This is getting us ready for the exam. And I'm even making it multiple choice. I'm giving you now a connection of a resistor and an inductor, and I want you to tell me, oh, and the E option is if I make a mistake. So Dr. Marsland would always say, you're betting against me if you choose that E option. That E basically would give him an out. There's no E up here. I'm just thinking of what's going to happen tomorrow. The E option is if during the process of preparing the exam I mess up, and those are not what I thought the answer might have been, I've labeled maybe as A through D, but I made a mistake, and you've worked it properly, and you go, this isn't right. Then you circle E. But Dr. Marsland used to say you're betting against him when you circle E. So if there might be a lot more E's this semester than in previous semesters. Now you're betting against me. Okay? But here we don't have an E, but maybe we should, now that I cooked this up quickly. What is the impedance? Now I'm using Z. What's the impedance across terminals A and B? And I want you to calculate that because I need an answer in about 30 seconds. And today you can discuss it with your neighbor. Tomorrow, not so much. But what is the answer? And I will ask you, A is 1, B is 2, so you'll be showing me your digits. I think I can see so far. I turned the lights up a little before class so I can see your answer. 1 is A. Maybe I should have said 1, 2, 3, and 4. But you're good at translating. Are we ready to show me your digits? What's the impedance across terminal? Okay, so now show me a yes or a no. Are you ready to answer? Yes? Okay. We have about 3 that are participating. When I say at the count of 3, show me your answer with your numbers, and maybe separate your fingers so I can see them clearly. Okay? 1, 2, 3. I see some 2s, I see some 4s. Which one is it? Why didn't I just write this down for the answer? That's it. Correct? It's the series combination of a resistor and an inductor. You just add those impedances. Your impedance of the resistor is the square root of 3. Your impedance of the inductor is plus j. But now I ask you to tell me what that looks like in polar form, which means just draw the diagram. If you now on your page, you could say, oh, I need to go over to square root of 3, which is 1.7-ish in the real direction, and I need to go up 1. So now I'm right there. That's my complex number, and you've written it in terms of a magnitude and an angle, and that angle is measured counterclockwise with respect to the positive real line. If I'd drawn that accurately, you should be able to see what the angle is. Is the angle 60 degrees? Probably not. Is it 40? Is it 30? That's looking more favorable. And what's its length? Well, you take the square root of the real part squared plus the imaginary part squared, and you get square root of 4, I think. So you get 2. The answer is 2. I'm sorry, B, which is 2 at an angle of 30 degrees. I think I saw more 2s than I saw other fingers. Are we comfortable with how you would find that tomorrow? So now I can probably combine things more difficult in a more complicated way than just a series combination. But now let's do the following. What's the current flowing in this series circuit if the voltage is 4 cosine omega t plus 15 degrees, and we have the same impedance across A and B? So you can use your answer from the first exercise, the first stretch. We now know that this impedance we can lump that all into 2 at 30 degrees, which was the same as the square root of 3 plus j. You need to be comfortable going from rectangular to polar and back. Now you need to find what is I of t in the time domain if the voltage applied to that circuit is now 4 cosine omega t plus 15. You need to make sure you're getting this, so talk it over, do whatever you need, but try to make sure you have a strategy, definitely in 24 hours, in order to solve this. We ready to answer? I think the frequency is omega. Yes, the frequency is omega. You got that right. And if I'm correct, the amplitude is 2. So that maybe gives you a hint. This is Ohm's law, just with complex numbers. The first step that you have to do is convert little v of t into its phasor. So do the phasor transform to get capital V bar. And what do you get for capital V bar? So wait. Let me get your answer first. We ready to answer? 1, 2, 3. I see quite a few 4s. I think 4 is correct. I think. Let's see. So what was V bar? 4 at an angle of 15 degrees. And what is I? Well, that's Ohm's law. I bar is now V bar over Z. That was now 4 at 15 degrees over 2 at 30 degrees. So we now just divide and multiply the magnitudes. 4 divided by 2, we get 2. And we add and subtract the angles. We add if they're all upstairs. We subtract those angles that are downstairs. And the way to see that, maybe, or think about that, is when you multiply and divide, hopefully you've converted things to polar form. Now put yourself on a circle and say, oh, I'm at 15 degrees upstairs. And think of it as an exponent. You now have 4e to the j 15 degrees. That's divided by 2e to the j 30. Well, when you divide numbers and they have exponents, that's like subtracting. So now you have 15 minus 30, or you have, for the angle, minus 15 degrees, which was the 15 minus 30. That gives you now your 2 cosine omega t minus 15. Where is this? This is chapter 9, but it's chapter 4 with complex numbers. So you just have to be comfortable playing with complex numbers and then just use chapter 4 material, or even earlier. What's z sub ab here? And you already know the first branch. So I have about half the class here. This half better get the question right tomorrow on phasors. Please come through for me. We're doing our exercises. We're stretching. Need to make sure. Oh, we'll stop stretching after this. Does everybody have an answer for z sub ab? Yes? Okay, show me your fingers at the count of 3. 1, 2, 3. Not so many fingers this time. What's going on here? So, how did you do it? Here is one impedance. You could say that's Z1, and here's another. This one is Z sub 2, and now Z sub AB is Z1 in parallel with Z2. And how do you combine parallel resistors when you just have 2? It's the product over their sum. Well, now you do that for these complex numbers when you have impedances in parallel. Now you have Z1 times Z2 over Z1 plus Z2. Upstairs, you're doing a product. It'd be nice to maybe keep those in polar form. The expression for Z1? Z1 was already given to us. What was that? 2 at 30? What's Z sub 2 in polar form? What's the angle? Where are we in the complex plane? Do you see where you're at? How far away from the origin are you with Z sub 2? You're 90 degrees from the origin, or that's the direction you're turning. Which way, up or down? Down. So now we're turning down, and how far are we walking? 1 unit. So now we're 1 unit away from the origin, straight down. This is now 1 at minus 90 degrees. And the bottom, well, that's now asking us to add. Maybe we keep everything in rectangular form. We know Z1 is the square root of 3, wow, square root of 3 plus J, and Z sub 2 was minus J. Ha! The J's cancel, and now we're just dividing by the square root of 3. And upstairs we have a magnitude of 2 at what's the angle? Minus 60. And so we should have C as our answer for that. Are we getting a little bit more comfortable with phasors? You're just playing with complex numbers, but applying your traditional strategies. So you might have to write a KVL equation. You might have to do a voltage divider. You might have to do a current divider. Now you just say, wait. Just block those pieces up into boxes and say, here's impedance 1, here's impedance 2. Let me treat those like resistors, and now I know how to work it with the appropriate magnitudes given by the phasor transform relationship of going from the time domain into the frequency domain. Questions relative to phasors? Then we will return from that stretching exercise and talk about chapter 6 into capacitors. Relative to what's the relationship between voltage and current, and now just to keep us grounded, actually we don't use common ground, do we? We don't use earth ground, we use a common ground. That's the ground we are working from. We're commonly grounded. But if we now say, oh, what does ice give us? We can keep ourselves help us out with that little sign on our piece of paper. I is equal to C dV dt. Now if I give you a DC voltage, what's the current associated with that capacitor? How much current is flowing through that capacitor? It's 0, because now if we differentiate a constant, that's what you learned in your math class. Now we have 0, so this capacitor has no current flowing when we have constant conditions. Capacitor acts, and when do we not have any current flowing? When we have an open circuit. That capacitor acts like an open circuit. What about this next case? Now we're going up and then down. And in this particular case, We are now charging the capacitor. We're applying voltage to it. We're separating charge, building up the charge on that capacitor, and then we're letting it go. We're discharging on the downhill slide, and the slopes, maybe they're not drawn accurately, but I'm going to assume that I slope up the same as I slope down. I go up y when I go over x, and I go down y when I go over x on the discharge. What's the current look like under this scenario? Ice tells me I need to worry about the slope, dv dt, and I have that on either side of t sub 0. During the charge phase, I now have a slope of y over x, but now I need to scale that by the capacitance, so that now I have this constant amount, which is c y over x, up until time t sub 0. And then what happens? Now my slope changes to a negative, and my voltage now, my current is now minus cy over x. And here I actually have a step change in the current. What if I have a step change in my voltage? What if V now transitions from nothing up to some value A1 at time t sub 0? Ice tells us c dv dt. And now what's dv dt? Infinite. Which means that we now need to go and recall our mathematical way of capturing that idea. And that's now to create this impulse, a Dirac delta function, A delta, and that occurs at the transition in voltage at t sub 0. Or somebody might just call that the impulse. And we're assuming that the area under that impulse is A. And that's going to depend on C and this step change in voltage. One more. What's I sub C look like for this application of voltage to our capacitor? It doesn't have any current flow up to time t0. Then we are getting almost a step change, but this is now an exponential. So we go up, but then what's going to happen after a fair length of time to our current? What's that voltage waveform look like for high values of time? It's flat, it's constant. And what's a capacitor do under constant supply conditions? When V is constant, dV dt becomes 0. So now we're going to 0 eventually, and that now allows us to do something like that. That's now our current waveform for that particular voltage waveform. And we'll finish with this question, and it has a two-part answer. Can V of t change abruptly in practice? No, since this would require what? Infinite current. But we allow for that mathematically, so we could say mathematically yes, since we can create this waveform, this impulse, delta of t. I'll see you tomorrow. Good luck studying and preparing, and then Friday we'll pick back up with Chapter 6.